Hello everybody, welcome to AP Physics. Today we're talking about momentum. So it's a pretty common word and sometimes it's used correctly, sometimes it isn't. If they say that the football team has momentum going into the second quarter or third quarter, what they mean is they've been doing well and they'll probably keep doing well. And that's kind of right. Because Newton's law, first law is things tend to maintain their state of motion, right? And so that's what they're talking about. So, if they say something is momentous, like CHS Philosophy Club, it's kind of right too, because momentum is very important too. But that's not actually the physics term, momentum. But it is very important. In fact, it's so important that we need to spend a whole chapter talking about it. And there's really only there's only two formulas in this whole chapter. Okay, so let's start looking at what momentum is. Momentum is a vector quantity. Momentum is a vector quantity, so that has size and direction. Mathematically, momentum is defined as the product of an object's mass and velocity. Okay, so inertia and momentum are close, right? Because inertia is the object's tendency to maintain a state of motion, which means if it has more mass, it's going to have more inertia. Well, momentum kind of takes it to the next level, and it includes the velocity. So, like I could have a truck coming at me at 1 meter per second, and I could maybe stop it if it was in neutral. But if I have a truck coming at me at 20 meters per second, I couldn't stop it. Well, that's the whole velocity part. And if you look at this, you can see that the m is not scalar. It's the velocity that has direction. Okay, so if you're wondering what the units are for momentum, you just look, well, mass is kilograms, and velocity is meters per second. So we get our units, kilogram meters per second, or Newton seconds is another label that we can use. Okay, so just so you know, when Newton was coming up with his ideas, we said Newton's second law was force equals mass times acceleration, right? But what Newton described force as is change in momentum per time. So we're going to talk about that a little bit later, how that ends up being mass times acceleration. But that's what Newton said. Because he knew if someone threw a ball at him, if it was faster, he'd have to put more force on it to change the momentum, right? And he knew that if it was a bigger ball, he'd have to put more force on it. So that's how he originally described force, was changing momentum. So let's just do some simple problem here. This one says, I'll see if you guys can do this. This problem says, what is the momentum possessed by a car with a mass of 2,350 kilograms if it's traveling at 125 kilometers per hour? Okay, good. So you guys, this conversion here, 125 divided by 3.6 is getting to meters per second. And this then is the mass. And so our momentum then is 81,597.2 kilogram meters per second. Okay, so we said that momentum is a vector here, right? And so we're going to have then a momentum in the x direction and a momentum in the y direction when we have, or we could have that. Okay, so keep in mind, the only piece that actually has that direction is velocity. Okay, momentum does have it because the velocity has it, but the mass doesn't. Okay, so if we look at impulse then, impulse is called J. So all the other letters were used up, so they said impulse is going to be symbolized with a big J. And that's what impulse is. So impulse, now this is kind of explaining what we were talking about earlier. The summation of forces causes the mass to accelerate. But Newton didn't say that. What he said was this instead. He said a force causes a change in momentum, and depending on how strong the force is, that change will happen over either more or less time. So this is Newton's first description of force. It wasn't mass times acceleration. But if you look at this, we can see how this comes out. So if force causes a change in momentum per time, change is always final minus initial, right? So this is our final velocity, our initial velocity per time. We can factor out our m, and this is another way to express change in momentum per time. This is what, right? Do you agree? Any questions on that? Okay, so then we look at our old kinematics equation, the relationship between initial and final velocities when there's an acceleration that happens. And if we're changing our velocity here, then there's an acceleration that happens. Okay? So we can then take this definition and put that in for our final velocity. And why do we want to do that? Well, because then we get our unknowns down to, well, we just have initial velocity instead of, two variables, final and initial velocity. And then we just do all the algebra, and we can see how things cancel out here. V sub naught minus V sub naught is 0, t's cancel out, and then it finally boils down to force equals mass times acceleration. So that's what we call Newton's third law now. Our second law is force equals mass times acceleration. But the way Newton described it is force causes a change. Force causes a change in momentum per time. Is that interesting? Okay, good. Well, you need to know that for the AP test? Probably not. Okay. So the question is, if we look at momentum being changed by a force, then we can say that a change in momentum here, change in momentum equals force times a certain amount of time. So when you look at the force and the time variables, what relationship do they have in this case? Change in momentum is constant. What happens to force as time is increased? So time gets bigger, what happens to force? Gets smaller. Do you agree? Have you guys ever heard of one of these? You know what that is? Yeah, a football helmet. It's not Homer Simpson. It's a football helmet, right? Can you tell now? Guy is throwing the football. So, you can't really see the face in there, but there's a guy in there. Why do we use a football helmet? What happens when we use a football helmet? What it really does is it increases the time of what we call the collision. And like, let's say that I have a football player that's running at 9 meters per second. If he hits a brick wall without a helmet, the collision might happen over, 0.01 seconds. That's going to be a pretty big force. Do you agree? Well, even if we can put a helmet on that guy and we change it to, let's say, 0.08 seconds, how much of an effect does that have on the force that he feels on his head? It's 8 times less, right? That's the whole idea behind that football helmet right there. That's why we have that football helmet. So we can put our heads in it and protect them. Hey, have you ever heard about the cars in the 1950s? and how they ran into the brick wall. Remember that? And then the cars in the, 2010s. What do these cars look like after they're done running into the brick wall? Well, the 1950s car looks like this. Little dent. Not to mention, very bad, sad person. And there's pieces of him all over. In the 1910s, the car looks like this. Do you agree? And what is that called? Crumple zone or crunch zone, or the cars now are designed to increase the time of collision. And if we increase the time of collision, we decrease the force, even though we have the same change of momentum. So that's what it's all about. So if you could see the person, you don't see the person in this car, you know why? Because he's over here kind of wondering what the heck happened. This one's dead. This one's wondering, mad. But he's still alive. Okay? So that's what it's all about. So let's look at this then. Here's your AP equation. So we have two equations now. Here's your second one. J, or impulse. Impulse is defined as force times a change in time, which causes a change in momentum. So this is the actual AP equation you will see on your AP sheet. And then the other equation that you'll see on your AP sheet is momentum is mass times velocity. That's all we have to work with for this whole chapter. 2 formulas, 2 days? Probably not. Okay, so the impulse momentum theory. So if you, this is from one of our books, page 167. A guy is hitting the ball with a bat. So what happens with the bat is, when the ball comes in, the ball actually squishes down at first, because everything has a little flexibility. So if you could look at the ball, it would be contorted like a spring. So there's a spring action in the ball when it hits the bat. And so at that time is when there's less than the maximum force. So that'd be like right here, right when we're starting to get that squish effect. And then all of a sudden, at this point right here, is when this ball is not going to squish down anymore. It's reached its minimum distance across the ball, or its maximum compression. So that's when we actually peak out at this highest force possible in a real hit or a real collision. This would be like everything. Because on the molecular level, we're all surrounded by electrons. There's always a spring effect in every collision. So you can do calculus to figure out the area under the graph, if it's a perfect parabola, which it pretty much should be, right? But what we do for this class is just take the average force times the time. And that will be our total impulse. Okay, so our total J is force average times how long that force was applied. Okay? So let's see if you can do a problem here. Give it a try. So not to mention that we've been moving along quite well here in this class, right? And now we're going to go a little faster. We're picking up momentum. Okay, so look at these two events. Both events, we have the 1,200 kilogram car, and we have the same momentum. Okay, so we're going to be running this car into two different things. One's going to be a boulder, one's going to be a haystack. But first of all, this is our change of momentum. Notice the negative sign there, very important. All right? Because if I'm coming, this will mess you up if you don't get your signs correct here. If I'm coming in this direction, I have a momentum in the positive direction, right? If I hit a wall, my change in momentum is going to be in that direction. Does that make sense? Because I'm taking away the momentum. And if you want to figure out where that comes from, well, the force to stop this car is going to be in the opposite direction. Just hold on for a minute if you can. Okay. So, momentum itself isn't going to explain what happens here in this collision, so we need to talk about the time that this change happens. So, I guess we're not going to run into a brick wall, but in one case we're going to use the brakes, which means we're going to extend the amount of time for that change in momentum, which means there'll be less force, right? So if you look at the math that happens, if it takes 12 seconds to slow down, look at our average force here is only 3,500 newtons. If you hit a boulder, it actually takes less. It actually takes less than 1 second, probably to hit a boulder, depending on what car you're in. But look at that difference. And you know what force does, right? So you know if someone forces on you that much bigger, it's going to do that much more damage. So that's what this whole force-time trade-off is when we're changing momentum and when we're having an impulse. Okay, so I want you guys to look at this problem, do that problem tomorrow, and then I'll have you do worksheet number 1 for your assignment for tomorrow. I'll have the answers online tonight. Okay, have a good day. Okay, for those of you that wanted to hang around a little bit and work on this together, just to kind of re-emphasize what we talked about here, these are both the same momentum change, but one has a huge force and one has a huge time. You know, the question is, if you were in a car, which would you rather have? A huge force or a huge time? Well, if you don't have a huge time, you probably wouldn't even know what happened. You might be dead. Okay. So let's take a look then at the next question. It says, by now this concept must be crystal clear since we have experienced a wonderful, amazing melon in a helmet and egg in a sheet demo, which we will experience in class. What impulse is required to stop a 0.25 kilogram baseball traveling at 52 meters per second if the ball is in the fielder's mitt for 0.10 seconds? So if we look at our formulas, we have J, which is impulse. J equals change in momentum equals force times change in time. Okay, so if it's going to stop, that means we're going to change all the momentum. So this product right here, so mass, change in velocity equals force times change in time. Our mass is 0.25 kilograms. Our change in velocity is 52 meters per second. And that equals it just says what impulse is required to stop. So that is the impulse. So 0.25 times 52 is the impulse. So 0.25 times 52 is 13. That is the actual impulse. Okay, so it's 13 Newton seconds. B, if the ball is in the fielder's mitt for 0.1 seconds as it's being stopped, what average force is exerted on the ball? So that is equal to force times change in time, which is 0.1. So the average force then exerted on the ball is 130 newtons. Okay, so you can do that. Hopefully you picked up some new information about momentum and impulse, and hopefully this helps you do your assignment for tomorrow. Worksheet number 1.